Word Gates by Eyal Ronen.
Right. Okay. So thank you very much. And this work is based on two papers where it was joint work together with Chichanok Yuval, but most importantly with our students, Daniel Katzman, William Koshak, and Gal Horovich, which of course did all of the heavy lifting, but they decided to graduate and move to other things. Don't know what is outside academia, but apparently they went there. So I'll be giving a talk. Okay, so in this talk, what we're going to do is we're going to talk a little bit about word gates on macroarchitectural states. We're going to define the logical state of the cache, and then we show how we can do computation on this logical state using what we called word gates. Afterwards, although this is, for me, a lot of fun and interesting by itself, for some reason, we need to actually motivate our work, except for the fact that it's fun to work on. So we're going to show how we can actually exploit the word gates, both for fun and for somebody maybe for profit. And we're going to show how we can do more complex computation. And we're going to show how we can use them to overcome coarse-grained timers mitigation for side-channel attacks. And how we can use them to break SBox-based AES implementations. All right, so we start by defining a logical state of microarchitectural cache. So we're going to start by basically associating a logical Boolean value with each memory address in the physical memory. And the physical memory address is going to be denoted as true if it's currently cached, and false if it's not in the cache. So we can start with the following assignments. We only have two addresses in the cache, both of them are true, everything else is false. Afterwards, we can actually set addresses to false by flushing them and evicting them from the cache, then setting their value to false. On the other end, anytime we're trying to access some memory address, it's going to set its value to true. There's a byproduct that we might also set another to false by evicting it from the cache, but this is a byproduct which we can work around. Okay. In order to actually see architecturally what is the value of a memory address, we can measure the access time, and this will observe its value. It will give true if the access time is short and false if the access time is false. As a byproduct, this is going to always set the logical value of this memory address into true. Okay, so we can set values, we can change the values of the logical state, but this might not be very interesting. So the question is, what else can we do? And we're going to talk about conditional access. Yesterday, in the Levchin Prize, we got two really nice recommendations for life. First of them was read, read, read. The second one was code, code, code. So we're going to do it, and we're going to read code. So we're going to start, and we're going to ask what happens if we run this process. So we have a branch where we access an input address. We check if its value is going to be 0, and if it's 0, we're going to return. Afterwards, we're going to take some pointer to our output address. We're going to do some really silly looking computation, just adding 0, it doesn't change the value. And then we're going to actually access this out address. And the question is, what is going to be the cache state of this out address after execution? So of course, if the value of the input address is not 0, then we're going to access output because we're not going to return, and the value is going to be logically set to true. However, we can ask ourselves, what happens if the input address is 0? And then it still might not be very clear. Let's assume the input value is 0, and throughout this talk, every time, all of the values of the memory addresses are always going to be 0. So we're going to assume this. And now, what the CPU needs to do is going to evaluate the branch. And this evaluation can take time because we need to compute. The CPU is efficient. The CPU doesn't want to wait. So what the CPU is going to do is going to predict the future execution. It's going to predict if the branch is going to be true or false. And if the prediction is correct, then great, we win. We don't need to wait for the branch to actually be solved, and we can run much faster. If it's incorrect, then we're a bit sad, but we don't lose by much. We're simply going to roll back the state of the CPU and try again with the correct value. So overall net gain for humanity. However, the note is that although architecturally, if we mispredict it, we're going to roll back all of the values of the register and the CPU state, the microarchitectural state still remains. We don't roll back this state, including whatever changes were done to the state of the microarchitectural cache. So even if input is equal to 0, this line of code can still be executed speculatively. And this means that the value of the output address will be turned into true. Now we're going to assume that the branch is always mispredicted. It's going to always mispredict because we're going to train it to mispredict. This is something we know how to do. And now we ask ourselves, will the output address be accessed or not? And now we might have two options. What we get is basically some kind of a race condition, because we have the part where we load the input address into a register. We're going to evaluate the branch. And on the other end, we have some delay instruction. This is the out plus equal 0, some not. And those instructions are the output address is dependent on those instructions. So the delay chain, what we call a delay chain, needs to be computed before we can access the outside memory. And then the question, what happened first? Can we get the input value? And if, for example, in is inside the cache, meaning its value, Boolean value is true, then it's going to be relatively short time to get it, short time to evaluate the branch, and then we can actually squash the speculative window and stop the execution before we get to the code line where we access the output address. On the other end, if input address is not in cache, it takes a very long time to access it, then before we are able to evaluate the branch and squash the speculative window, we are already going to run the code line that accesses the out address and change its value to true. Now, if we look at it, we can see that we actually have a truth table that says for every Boolean value of input, what is the Boolean value of output after this gate. And this is actually a NOT gate. So here we can see we can actually do a circuit, a simple electric gate that runs on the microarchitectural state. Now, NOT gate is nice, but might not be that interesting. So we can build some more complex gates. And for that, we need to think about what is this, how is this gate works, how is it built? And what we see was basically, we have two chains that runs, and we have this race condition between them. One chain is the signal chain. This is what actually accesses the output address in the end. And one is what we call the control chain that evaluates the branch. And we have a race condition between the both of them. And we need to have some delay instruction in order to make sure that the race condition is one only if the input address is in cache or not. And we have the probe that actually checks the cache value of the input addresses. So now we can actually combine several such chains. So for example, we can have the following code where we have where we check if the sum of two input values is equal to 0 or not. And now we can use the same view, and we can see that if a single address, input address, is not in cache, then it will take this branch a long time to evaluate, and we will be able to access the out address. Otherwise, if both addresses are in cache, then this will be resolved quickly, and we don't access the output address. And again, we can have the truth table of this gate, and we can see that this is actually a NAND gate. It's only return false if both input addresses are true. And the nice thing about the NAND gate is that we can use it to actually build any kind of circuit. So this allows us to compute any arbitrary circuit on the microarchitectural state. Now, I lied a little bit because we have an interesting phenomena here. And the thing is that the computation that we do is destructive. Because when we run a gate, then we always access the input addresses. And this means that their logical value is going to be set to true afterwards, regardless of the original value. And this means that we can only use an address input once. Afterwards, this is destroyed. So we need ability to build more complex gates where we have a single wire that is an input to several different gates in parallel. And the way that we do it is by increasing what we call the fan-out of the gate. And this is relatively simple. We just access several output addresses in parallel. And this means that we can duplicate the output address. And we can actually build what we call fan-out gates, which take a single value and copy its state into several other addresses. Okay. And although we can use NAND gates to build whatever we want, we sometimes want to have some more complex gates in order to make them more efficiently. So this is a very interesting computation, which is very clear to understand the truth table. And in the end, I will translate it. This is the knot of a majority gate. And the nice thing about this is that this can actually be used to do error correction on our computation. Because we run things on the state of the cache, and this is noisy, we have operating system and other processes, we might want to repeat several computations and then do error correction on the results. And this allows us to do it relatively efficiently inside the microarchitectural state. Okay, so now I told you we can do weird gates. I think this is really cool, but it's not enough to convince reviewers to get papers accepted, and we need to show them that this can actually be useful for something. So now we can talk about what we can do with circuits. So for example, we can do 4-bit ALU inside the microarchitectural state. We can do SHA-1 computation. This is nice because if you want to do some obfuscated computation that is very hard to debug and understand it, then we can do everything inside the microarchitectural state. But maybe more importantly, we can actually play the game of life. And we can do it for several generations. And this is basically the heat map of the output of the results for several inputs. For me, this is a good enough motivation to do the research, but we work in crypto and security, so we need to have some security implications, which game of life doesn't necessarily have. Okay, so let's talk about flash reload. Everybody knows and loves this attack, square and multiply. You can do it on RSA, Diffie-Hellman, El-Gamal, whatever is your favorite exponentiation algorithm. So this is an example of attack on RSA, I think, and we can see that the difference between the cache hit and miss of this attack that we do is roughly about 40 nanoseconds, which is a relatively short time. We can measure this timing difference when we have access to native code on, for example, Intel x64. However, this was also noticed by, for example, browser developers, and decided that if we want to mitigate this type of microarchitectural attacks and speculative execution attacks, then maybe we just prevent anyone access for high resolution timers. So if we look at Chrome, we can only have access to 0.1 millisecond timer resolution. Tor, which should be more secure, has 100 millisecond. And even on native code on Apple M1, we don't have a very high resolution clock. So this makes it much harder to do this type of attacks. And we want to be able to reduce the required time resolution. And actually, we want to be able to measure this photo finish type of timing difference with maybe even a wall clock. And microarchitectural gates can actually allow us to do this. So what we're going to do is basically we're going to amplify the signal. So as a primitive, if we have a NOT gate with a very large fan-out, we can basically take the logical state of a cache address, if it was inside the cache or not, and copy it to 8 output addresses. And this gives us an 8-time factor in the timing difference from 40 nanoseconds to 320 nanoseconds. This might still not be enough, so we can use this tree structure to increase it to 64, 512, 4096. In real life, this even might not be enough, and we have limited space where we can do the amplification because the cache size is limited. So we have a nice hypertree structure, which allows us to basically increase it to arbitrary values. So we can now copy the state of a single cache hit or miss, and do a computation where the timing difference between this cache hit or miss will be 0.1 seconds sometimes, and we can actually go much higher than that. But now we're able to amplify, but this is only half the job. So now we can differentiate between the single hit and miss. However, we want to attack native code exponentiation, and the timing difference that we need to, the temporal resolution of the attack needs to be about 25 microseconds, We can increase the RSA size. Maybe we'll use 6,000 bit RSA. It will make it a bit slower, but this is still much faster than what we can do when we do amplification. So what we're going to do is basically allow us to do high resolution prime and probe, sample in a resolution that's much faster than the clock that we have. And the main idea behind it is that if we look at prime and probe, we can see that this is actually a type of a NAND gate applied on the eviction set. Think about it or read the paper, you will see it. So what we're going to do is we're going to repeatedly probe our eviction set, which means just applying a NAND gate, but each time we're going to store the result in a different memory address. And we're not going to measure the result. We don't know when the cache hit or miss what happened, but we're going to store all of this in memory. And after we finish the attack, then we're going to amplify. This decouples the probing from the time measurement itself. Now, this introduces some more complication because we can't actually store all of the samples we need for example, for full RSA or L-Gamal computation, but we can measure large enough chunks of the attack and then stitch them all together. And we were able to attack a square and multiply L-Gamal with a 0.1 millisecond clock. Which again, it's basically the clock time is pretty much the time it takes to run the entire attack. Okay, so this is nice, but this is not all. This raises the natural question of how fast can we probe? What is the fastest resolution for macroarchitectural cache attacks that we can do? And so far, the state of the art was with this really, really nice paper called the Prime and Scope from CCS 21, and they had something that is almost optimal. They only need one access to L1 cache to see if something is inside the cache or not. However, this access is about 5 cycles, and the resolution is 70 cycles. And ask yourself, where does this overhead comes from? And if we look at it, it's basically, again, the time measurement that we need to do. Measuring the time is order of magnitude larger than the actual thing that we try to measure. So we have the primary store. This is our hammer. Let's try to use it on this nail. So after some optimization and finding a very efficient gate, we can actually improve and get it down to 48 cycles, which is nice. It's better than 70, so we win. But it is still an order of magnitude larger than those 5 cycles that we actually want to get to. So what we do is we're going to use the same idea of gates, but now instead of sampling an input address once inside the speculative gate, we're going to repeatedly sample it over and over again inside the speculative execution. And if all of those load addresses are going to be inside the cache, then we're going to return before any of the delay function returns. However, if somewhere inside if we get a cache miss at some point, then all of the accesses before it are going to be into memory, and we can actually detect which of those loads was the one that gave us the cache miss. We have nice graphs that show that we can actually get a resolution that differentiates between 5 cycles offsets. And we can use it to attack S-box AES, which is a much harder target than the regular T-tables because it's a much smaller table and which we access much more. And we need to distinguish the exact AES round. And we need a very fast sample rate. And PowerWork needs some non-trivial assumptions to do it. We were able to do it by actually measuring the exact round, which we did not by measuring when the computation started, but we actually measured the time difference between accesses to 2 different S-box cache line, which are about 10 to 20 cycles, CPU cycles difference. Okay, and we were able to attack it. Requires about 10,000 traces, and everybody are happy. Okay, so to summarize, microarchitectural weird machines are a thing. It's very fun to work with. It can actually have some security impact. And we think that it's a new emerging area, and there's a lot of work to do in it. So if you're interested, I'll be happy to chat, and I invite you all to have a look at it. Thank you very much.
Okay, maybe one quick question.
So it's a great attack. The question is how to mitigate it.
Right, constant time code, basically. This is the best answer I can give. This is, actually, we disclosed all of these attacks and everybody said, all of the vendors said, okay, but this is not a vulnerability. This is how the system should work. The vulnerability is in the code. We said, okay, we agree, we can publish faster, everybody happy. If you write secure implementations, then this attack will not matter.
All right, maybe a future paper. Thank you very much.